So in our chats about atomic models, we first chatted about Dalton, who had the indivisible atom, the billiard ball model. And then we found Thomson, who discovered the electron and stated that the electrons are embedded in this positive goo or sphere of influence. That invalidated Dalton's model, because Dalton said the atom was indivisible. So what we want to do is we're going to progress along. Now we have a Thomson model. Let's see what's coming next. So first thing is, this was at the start of the 20th century. This gentleman named Ernest Rutherford, he performed this famous gold foil experiment. So here's what he had going on. So inside a lead block here, he had a radium source, which is radioactive, and this radioactive source was emitting alpha particles. So we have this little hole here to ensure that the alpha particles travel in a straight line. So these alpha particles hit a little thin piece of gold foil. And then past the gold foil, we had a zinc sulfide screen, and the screen was just detecting where the alpha particles hit. Now, for the most part, wasn't particularly interesting. Most of the particles passed through with very little deflection, kind of hit right, over in this region. Some had a little bit of a scattering angle, but you had the occasional one that had a really large scattering angle, like they would have kind of almost reversed course, like they might have hit the foil, ended up back here. That one was a little bizarre, because you want to think of it. Thomson's model stated that we have this positive region of influence kind of spread throughout the atom with these electrons embedded in. So by Thomson's model, what we should expect by passing through these positively charged alpha particles, they should just pass through straight or with very little deflection, and that should be all that's observed. This was not what Rutherford and his team observed, though. So as we said, most of the scattering was very minimal or none at all. Like most of it was confined to about a degree or less, but there were particles that scattered drastically, and Ernest Rutherford described it as this. He basically said it was kind of the same thing as if you took like a 15-inch bullet, fired it at a piece of toilet paper, and the bullet came back at you. So that was the level of astonishment they had with this. Now, that led to a bit of an issue, though. They had to explain why the results were as they were. So Rutherford figured out that there had to be something wrong with the Thomson model. It couldn't be that the positive charge was spread out kind of uniformly. There had to be something a little bit more in depth on that one. So what Rutherford eventually figured out, though, is that positive charge isn't spread throughout all of the atom. It's actually concentrated in a very tiny volume. So what we have here is the Rutherford model. We have this positive charge confined to a very, very tiny volume. So when most alpha particles pass by far away from this positive charge, very little is going to happen. But when you get that occasional one that gets really close, it's going to be repelled, and we're going to see those very large deflections. Now Rutherford, they tried scattering alpha particles from other metals, so they changed gold to different metals, and they found the same thing. Most of the alpha particles had scattering of about a degree or less, but you had the odd one that underwent some extreme scattering. So what Rutherford had showed is that the positive charge and most of the mass, it's contained in a very small volume with a radius of less than 10 to the minus 14 meters. So Rutherford and his colleagues, they discovered what we now know as the nucleus. So the nucleus of an atom is where the positive charge is contained. It's really small. Most of the mass of the atom lies in there. So Rutherford's work disproved Thomson's model of the atom. So Thomson's off now. Now we have the Rutherford model. That is now the model of the day. So let's look a little bit more at Rutherford's model. So his discovery of the nucleus basically led to the Rutherford model of the atom. Sometimes we call it the planetary model, the solar system model, or the nuclear model. So basically in this model, we have the nucleus at the center, and then we have electrons orbiting around it. So when you see kind of like that stereotypical cartoony picture of the atom, kind of like on the front cover of your notes, that's actually the Rutherford model. And most people, when they think of an atom, that's what they're thinking of. Not quite correct, but hey, it is what it is. So we can actually determine the size of the nucleus, and Rutherford was able to do this by applying the law of conservation of energy. So the only thing that we need to add to our tool belt is we know how to find kinetic energy. It's still half mv squared. That part has not changed. But what we have to be a little bit more careful with is potential energy. So this equation, if you ever need it, it would be given to you. But for electrics work, electric potential is given by this K, Q1, Q2 over R. Looks really close to Coulomb's law. It's almost identical, and that's not a coincidence. So EP is going to be the electric potential energy. So we're going to have K is Coulomb's constant. Q1 and Q2 are going to be the charges. And Coulomb's, and R is going to be that distance between the center of the charges. So this equation is actually derived using calculus. We don't need to know that for physics 30. So one of our big assumptions that we make is that if we have two charged particles, if they're really far away, or we could say that they're infinitely far away, we say that the potential energy between them is approximately zero. Not quite zero, but it's close enough to zero. So let's look at this in an example. So we have the charge on a tin nucleus. It's plus 50 times the elementary charge. So we'd like to find out how close can an alpha particle with an initial kinetic energy of 1.6 picojoules approach the nucleus of the tin atom. So kind of here's what we got going on here. So here's our tin atom. Here is our alpha particle. So alpha particle is over here. We know that its kinetic energy is 1.6 picojoules. And then a little bit later, we'd like to find out how close does it actually get. So we have our alpha particle, we have our tin nucleus. We would like to find that distance, rather the distance between their centers. That's what we'd like to find. Now, we're going to make an assumption. So the assumption here is that to begin with, we're going to assume that the alpha particle and the tin nucleus are far enough away that we can assume the potential energy between them is zero. So they're far enough away such that EP equals zero. So what we're going to put here is we're going to put the potential energy at this point is zero. Now, I have kinetic energy of 1.6 picojoules. I have potential energy of zero. So we also know just from, studying energy and mechanics in physics 20, mechanical energy, the kinetic plus the potential, is going to be 1.6 picojoules. This does not change because we are using the law of conservation of energy. So that doesn't change. Now, when this thing gets to closest approach, well, we're going to assume at closest approach, at closest point, alpha particle stops. So if the alpha particle stops, we're going to say that its speed is zero, which allows us to say that the kinetic energy is zero. So if we know at this point that the kinetic energy is zero, and we know the mechanical energy is not changing, it's that 1.6 picojoules, that is going to tell us that at this point here at closest approach, that potential energy between the tin nucleus and the alpha particle, it's going to be 1.6 picojoules. So what's happening here is as this gets closer, all of that kinetic energy is being converted into potential energy. So we know at the point of closest approach, there is 1.6 picojoules of potential energy in the system. So we know EP is this K, Q1, Q2 over R. This is going to allow us to find R. We know K, we know the charge on the alpha particle in the tin nucleus, we know EP. So R is going to be this K, Q1, Q2 divided by EP. So K is our Coulomb's constant at 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. We are going to multiply that by the charge of the alpha particle, which is twice the elementary charge. And then our tin nucleus has 50 times the elementary charge. And then we're going to divide that by the potential energy, which is 1.6 picojoules or 10 to the minus 12 joules. So we've got a lot in here. We've got to be really careful. So we've got our 8.99 times 10 to the minus 9. We've got our 50, or twice the elementary charge. Then we have 50 of the elementary charge So what I'm going to get here, ooh, that number looks way too small. There is no way that that's correct. Oh, yeah, that would make sense. I put in E, this is negative, so this should be positive. Yep. So what we're going to get here is we're going to get about 1.4 times 10 to the minus 14 meters. So what this is telling us is that this alpha particle, the closest it can get to the tin nucleus, it can get to about 1.4 times 10 to the minus 14 meters. After that, the electrostatic repulsion is not going to allow it to get any closer, and then it's going to move away because they're both positively charged, they're going to be repelled. So we used conservation of energy to do this problem, but again, we had to give you that formula for electric potential energy because that's not something that's not an equation that you are able to derive in Physics 30 because you don't have calculus or you're not required to. So we give you that equation. If you ever need that equation, we will provide it to you.